picture of the. Oh, from here. Yeah. I would do it, just as a kid, right? But it's all. I'm so sure. Yeah. I did a lot of Casper. I did interview. So. Wait, how did you make that? Find somebody to hate him to that is how you do that. What did you interview? Sounds. Your parents are not bad. They just. Yeah. I got a friend that's 56 years old, so I was probably sponsored. Okay, so yeah, it means that, you know. He was born around 72, 74. So that's he's old enough. But I think she gets very. What's up? Two little necessarily struggle to use the after coaching don't make things. I don't see how people struggle. Yeah, that's what we're constantly. It's just, it's hard to get all the way to solving that it's all just microscopic process of quality. Especially this is the exact reason why people struggle with can't see it. Yeah. That's why it's long.
So anyway, let's start then. Yeah. So last week we talked about different ways to connect the transformer. So in here we just have a quick review when we able to connect them in series in primary side and secondary side. We call it SS. So we got various type of conversion ratio. Like in this case, because in the input side and output side, we always double the voltage. So the actual voltage conversion ratio will be still N2 over N1. So we're also making various type of the conversion ratio. When we have 1 to 3 and 1 to 2 connect together, in this case, we just work on the voltage conversion ratio, we can get conversion ratio to 5. In this case, when the winding become opposite to each other in the secondary side, then we're able to produce conversion ratio equal to 1. And hence we're able to get other conversion ratio, 6 over 5, and also 6. So that is to say, for two transformer connection, if they have different voltage conversion ratio, we're able to produce various type of the voltage conversion. That could be quite interesting. Yeah. Only two transformers. And then if we put the output and input swap them, then we're able to reverse the voltage conversion ratio. Because for transformer point of view, we sell only a mechanical, electromechanical substance. So we flip input and output. So it doesn't really matter because they both have bidirectional power flow anyway. So that is to say, if the transformer conversion rate equal to 6 over 5, then actually when we flip them in and out, then the conversion ratio becomes 5 over 6. So you can test them, you can try them, you can see that phenomenon. For instance, if you have a transformer 110 volt to 220 volt, if we reverse them, then voltage conversion ratio become half. If forward them become double. So this is a common way we can operate on a transformer. And then last week, we also mentioned about auto transformer, which is able to connect a transformer input output using the same winding. So in this case, you can save the copper. Instead of using two winding, we can use single winding. But the key thing we observe from here will be not only we can reduce the operation, reduce the configuration, we can also reduce the current sharing in this winding. So in all this example, we can see that the winding of the common winding, we have less current. Either compare the output or compare the input, we can have less current. So that's one of the things you can see that we also examine one of the transformer example too. And then we also discussed briefly about connection of transformer, say three-phase transformer. We got the star and delta connection. So Y connection we call star because it has three winding in such a way we have midpoint connection. You can see that this midpoint connection create us with a neutral. So in three-phase system, I think you do learn briefly. Have you learned about the three-phase last week? No, you haven't learned any three-phase system, right? Okay, I thought you had heard it. Anyway, but so you're going to learn the three-phase system question in the electrical circuitry, electronic circuitry anyway. But three-phase system, you can imagine we have a single phase in here, only provide you such voltage. And then we found that if we're able to create another same voltage, but displayed by phase angle 120 degrees, that's the second phase. And then another third phase will be another 120 degrees. So you can see that now we have a three-phase system. In here, we display by each by 120 degrees. So actually, when we generate power to you, to the user, we simultaneously produce three types of voltage. They are same frequency, usually with same amplitude, but all have a phase angle 120. So they're quite symmetrical. So in this case, why we do that? Because in terms of our generator or machine that can create three-phase balance. You can see that if a machine only single phase, then the power may be biased to one certain point. The machine may not be too stable. But if a three-phase system, they all display by 120 degrees, even though when we rotate them, each of the phase, if their current is the same, in this case, they are more mechanically balanced. The system, even the bearing inside the system rotation will be more balanced. In this case, we all prefer to have three-phase system. Of course, we do have many other advantages using three-phase, because for electrical point of view, when we rectify the three-phase into DC, like in here, I think I did mention to you, have single phase, when we rectify, then become this. Then when we change them to DC, what we need to do, we change all this voltage in DC, we need to fill up this gap. That will require a big capacitor to fill the big LC filter to do that. But if we're talking about three-phase system, then the voltage will be more like this. And then when you rectify them, then they are more like they fill up all the gap in here. So that means we then filter them into DC, we only need to fill up this little bit of the gap. So that is to say, even though the LC filter, we use the filter, this kind of ripple, the demand for the capacitor and inductor only very little. So that's to say, for high power system, we always use three-phase. That's why you can see that the cross-country power transmission, when you see outside, we always see three cable there because three-phase voltage. So, but anyway, that gives us a really quick review of the three-phase system. So for transformer, because we also need to change the voltage. For transmission, we usually use really high voltage, talking about maybe 1 million volt of voltage. Instead of 110 volt, 120 volt here, we need to step up to really high voltage. The only thing you can do that is to use transformer. Probably this is a transformer can be stepped up or can be stepped down the voltage. Because for transformer efficiency, I told you about 90-something percent, 99% is not difficult. So that's why if we use them for transmission, we don't really care about the power losses when we change the voltage because the efficiency is really, really good. So in this case, we usually use the transmission line to get a transformer, assist us for power distribution and transmission. Anybody will tell me why we need to use high voltage for voltage transmission? Yes?
Because current causes power loss with the since the power loss equation is current squared times resistance.
Yeah, that's right. Yeah, because such a huge power, gigawatt, megawatt, tegawatt power, then the current can be huge. But maybe increase the voltage to a few, maybe million times, then we can much less current anyway. The power loss, I square R is the losses, we can reduce it. So anyway, so the transformer key application for transformer will be this kind of way. So that means transformer Although we learn single phase here, but when we put in three transformers together, become three phase. For the detail, you'll go through them in the electrical circuitry for a three-phase system. But in here, I just show you the configuration for three-phase transformer, how they look like. So probably you can see that for three-phase transformer, we got three winding, basically three winding. We can allow them to configure them into star connection. Like here, we got three winding. We connect with a star connection, or sometimes we call it Y connection. And then for another way of connection, we call it delta connection. So that means for this, you can connect it in delta way. So remember, we have dot location here to tell you how we start the polarity or start the winding. So in this case, just show you the polarity of each one of them. So that means if that is 0 degree, then this will be 120, that will be 240 or minus 120, and so on. But transformer, because we have different way for connection, star or delta. So in this case, when we put transformer primary side and secondary side, we can either connect in primary side in delta or star, or secondary side delta or star. So totally 2 times 2, we got 4 kind of the arrangement, a combination. So you can see that in my lecture notes here, I have 4 types of the configuration. So for instance, the first one, Y to delta, the second is delta to Y. The next page you can see under combination. So each one of them has different kind of the specific application, but of course, in the detail, I can let the other professor in the electrical circuitry to explain to you. But briefly, you can see that the voltage, three-phase voltage relationship to input voltage is V. And then when we display by this kind of star arrangement, this voltage will be V over √3. Have you learned that in equation? Yeah, single phase to three-phase combination. Have you learned all that? No, you should have learned that in the first 2 years. But anyway, but the detail, if you check any internet, there's a million of the literature to tell you how the voltage relationship between single phase and three phase. That's quite straightforward, but I don't tell you in detail. You go home to get it back. Let me know on Wednesday.
Does it have anything to do with the RMS?
Not only this, mainly is something about the vector, because each one of them are 100. This phase angle 120. Then adding 2 vectors together, 120. The resultant voltage across here is not direct summation, but vector summation. Because 120 voltage angle, when adding 2 together, become this voltage. That's mainly about this, mainly a vector sum. Because they are not DC. DC, you can just add them together. But for a vector, you see 120 angle, we can still call it vector. But the vector in the point of in the electrical circuit vector. So the summation become this arrangement. But anyway, so let's delete immediately. This is V voltage. And then this phase voltage in here will be V over √3, 1.7 something. So that's voltage. And then in here as well, we got this voltage, but because the delta connect in such a way, you can see that this voltage are equal to the phase voltage. Just like I say, this is a phase winding. 2 phase winding add together become input line voltage. You get that? Yeah? And then, but this voltage will be slightly less by the ratio of √3. And then if we connect them in delta, then this input line voltage, right, is equal to its phase voltage. So that's why I can see the arrangement. By different connection, we're able to arrange the actual voltage appear on the winding, relate to the input voltage, or relate to the output voltage. So that's, you can see that. By using this method, I can adjust slightly about the voltage appear on each of winding. For instance, if this voltage will be 1,000 volts, so this voltage is not 1,000, but 1,000 divided by 1.7 something √3, right? So this is slightly less voltage. So that's to say, even though I apply the full 1,000 volt to this transformer, the actual voltage on here will be slightly less. So that means the stress or the current, maybe the magnetic loss, will be slightly less. So that's the one we can see that. But we have arranged in this one, all this voltage and clear directly to the winding. So there won't be any free reduction. So that is to say, if I apply some work, maybe apply a motor, if there's a motor, you see motor and transformer are quite similar. If I apply the three-phase voltage to a motor, then initially when the motor did the standstill to start, the motor current can be quite huge, which you don't quite like that. Huge current, you can damage the winding, cause a lot of heat, a lot of something. So if this motor, when it's starting motor, I may prefer to use different winding, like in here, if I have full voltage, I actually apply for this motor. I don't want full voltage. Instantly apply for this winding, it may damage winding, because when the motor is standstill, inside the motor doesn't have any resistance to the input voltage. We call it back EMF, which you can learn it in a moment. Then I'll teach you the DC motor. So all the motor that stands still, because it doesn't have any back EMF, it cannot against any input voltage. The current will be really huge. So that means when we start on any motor, the initial current is really large, which we don't want that. You want to protect it. One of the methods will be when you apply high voltage in here, we start the motor or arrange motor in this star manner, so that means the motor winding has slightly less voltage than the full voltage. That's one of the methods we can use for many startup circuitry for a motor. So when motor after start for maybe half a minute, when it becomes more stable, we can change the connection quickly into this arrangement. Then you get full voltage applied to the motor. If the motor already full running, so in this case, the current becomes less. So that's one of the ways we can swap from star connection to delta connection. So that's one of the examples why we sometimes we need to use star connection, sometimes we have to use delta connection, mainly about to control voltage and current on the electrical machine. You get that? If anything you don't quite sure, just let me know, because I thought you have learned the 3-phase. It's luckily you tell me you haven't quite touched of the 3-phase yet. But anyway, you're very sure after a few weeks, you're really 100% familiar with the 3-phase system anyway. So that's our arrangement. You can see that you can now have Y to delta and delta to Y configuration. And you can also see that usually for 3-phase voltage, we only need 3 wires. That means, for instance, we call it the L1, L2, L3, 3 wires. And this neutral point, we not really need a connection. Why is that? You can see outside in the cross-country transmission, usually you can only see 3 wires. You don't need 4 wires this one. Why is that?
All of it added up will always end up with 0 in the center, so that's just the ground plane.
Yes. All the 3-phase voltage, especially high voltage, high power transmission, supposedly they are balanced really well. So that means there's current here, there's current here, there's current here. We don't need any current, we all bound cancel out. If no current, what's the point to have a line there, wasting the material? We don't need to do that. So that's the key point. So that's why for even for delta or complement, we certainly don't have only neutral here. So for high power transmission, usually we do have the only 3 wires. But having said that, you want to add something?
Oh, no, I just have it.
Okay. So that means, so usually for all the transmission distribution, we only need wire. But however, for many buildings, we can still see this neutral point. Why is that? That would assist the building to create a neutral, to create a 0 voltage. So that usually will be 0 volt. We try to make it very close to the earth, the ground. I think when you do with some hardware, like I'll be talking about the ground connection, that's for protection. So we use this point, we try to make it short to the ground voltage in some location. So that's another electrical safety. A little bit more complicated, but usually in general side, in the substation, we try to create a neutral from the 3-phase, and then this will be connected to ground for electrical protection. Protection is another big topic. Probably we are not able to cover here. We can cover it when we do more study on power electronic electric vehicle or safety system. So anyway, so this is 0 volt, there's a certain voltage, 120, 24, 40, so on. So then roughly you can see the arrangement for three-phase transformer. So they have a very method of the connection. Now in here, you can also another connection like delta to delta and star to star. Again, they all have various way of the application, the detail how to use them, mainly because how we want to arrange the voltage. Sometimes we got more voltage and less voltage. That's mainly how we do that. But more interesting to see will be how we put them into a transformer, how to do the winding. So basically, you can see that for three-phase transformer, we have three winding, right? Three-phase winding. You call it maybe A winding, B winding, C winding. You can arrange in such a way. Then you can see that each of the winding, the generate magnetic flux are looping in such a way. But if the three phases are balanced, even though the flux are also in three phases, they also balance to each other. So the summation of all three phases should equal to 0 anyway. So you can see that all the flux now are looping into center here, then the summation of flux equal to 0. So that means central limb in here, the flux should be negligible or really small. So that's how we can see the arrangement here. And then you can also see that another way of the common transformer core would be so-called E core. So E core, we got three limbs here. Each one will have their own winding, phase A, B, and C in here. So one thing we can see that, how about the primary and secondary? Well, obviously you can see that we are putting each of phase, they will have their own primary and secondary winding. They all should be putting on the same core limb. So they all putting in here. So that means the primary, secondary all wind on here. So, but what do you think? Do you think we used to put them one on the top of each other or not the case? What do you think? How do we do the winding? Primary and secondary? Do we like this diagram on top of the others? Any comment? Of course, the left, you put the two transformer on either side. But shall we do that?
Does it make the difference?
Yes, big not of difference. In theory, in the textbook, probably they don't tell you much about it. But for practical transformer, that will affect a lot of the performance. You could have power loss, the leakage field, anyway. So in the textbook or in the lab, we just make it easier. Then the transformer you can see will be something like that, right? Probably in the textbook you can see we have transformer, single phase, right? So you got primary here, secondary here. So primary, secondary. So that's how we written down in the textbook, right? But however, that's not the case. But we usually putting them together in such a way. So you can see in here, if you look at in this direction, you can see that we firstly we put in primary here, and then the secondary, we putting just slightly surrounding on the top. We're all putting together. Why we do that? Because we want to ensure the two winding can couple to each other really well. If it's more close to each other, the coupling will be much better. For instance, when you do the lab, then you can redo the lab by putting two winding together. So that is the lab, what you did in the lab, right? But if we do the lab here, putting all the winding primary and then put the secondary winding on the top, then you can measure the leakage inductance. You can find that they should be small. If you like to get high grade for your lab report, you can do some extra. I mean, there's no limitation. On first day when you do the lab test, conduct more tests. You think you can able to get high grade, then you can always to do more tests. So you can see that the different. Then you may ask why we have different transformer. The circuitry look like this, right? And supposedly they are on either side, but that's not the case, right? This is a magnetic core. We just mean we put the winding on the magnetic core, and then it generate the magnetic flux. The flux will couple to secondary side. We need to have them couple much better. So if they're on either side, we have something happen. The leakage field will come out. Just like the model you see, the leakage field will circulate along the winding, appear around the winding. So we try to enclose them so that all the field can be coupled between primary and secondary really well. If you put them together, we find that experimentally they can couple to each other really well. So that's what we're trying to do. So the best thing is to like this thing together. Like this 3-phase transformer, you always put primary and secondary here for the phase 1 and phase 2 like that and phase 3 like that. That's the best way to do that. And then the thing is, the higher the coupling between the primary side and secondary side, you got higher efficiency anyway. So that's how we do a transformer with 99%. If you don't do that, probably the transformer we make only about 95 or 90%. Anyway, yes.
What is the difference between this and having 3 different like 1-phase transformers for the 3-phase?
What if I have 1-phase transformer for?
Like the transformers like where there's only like 1 loop and 1 primary, 1 secondary instead of like E shape or the Y shape? Could you just do that? Just have 3 of those?
Into a single core. You mean?
No,
When we-
like three cores.
Yes,
And
that is
with
next
3
page. When we construct a 3-phase transformer using 3 single-phase transformer, you can do that. You can use 3 separate core to do the job. But in here, why we like to introduce this concept to you, because we can see that we got cancellation of flux, like in here. You see when the flux in here, they all go into the center limb here. The key advantage will be we can use much thinner center limb magnetic material. We don't use thicker one. In theory, this area equal to this area, he will just putting 3 transformers, separate transformer together. But when you join them together in such a way, you don't need to have a free area in the center. We can consolidate them into really thinner magnetic limb because they don't have any magnetic flux. They all cancel out anyway. So you only need something there just in case any leakage flux or any unbalanced flux in the center. So that's one of the ways why we want to put 3 phase together. We can reduce over all size for the transformer. If like what you mentioned about, if we're using 3 transformer like this, then we have to use 3 separate magnetic core. That will cost you additional material anyway, because we know the center limb, they can cancel out all the magnetic flux. We can therefore reduce the material.
Is there like a efficiency difference between them?
Yes, of course. That's a really good question. You see any material in here, if we travel this path, then any magnetic flux, they can cause some magnetic loss due to the magnetic flux travel, just like current. Current pass through a resistor, there will be resistive loss anyway. Magnetic flux pass through any material, there will be losses due to the hysteresis losses or eddy current loss, which will go through them in the next few slides. But anyway, there must be losses. Although you can complain to me, oh no, here the flux is so little flux, it doesn't bother you, right? But the thing is, this flux may not be bothering us, but however, the flux still need to travel along here, still need the cancellation, still need additional material, and the flux is not balanced, we have still some wasting in the power losses. So we try to, in all the scenario, try to reduce as much losses as possible. So that's why we'll think that this Y type transformer, we will be able to use thinner type in here, can reduce the losses. But if you have 3 separate transformers, all the magnetic flux will pass through all the whole loop, then certainly we got more losses. We don't have any cancellation. Once you cancel all the flux, we got 0 flux in certain location, we must have 0 losses. So that's how we do that. So remember, when we have 3-phase transformer using the E-core types, we are winding in such a way. Primary, secondary, and so on in here. Then of course you may say, oh, this flux have to travel longer distance. Yes, it have to travel longer distance. Then that is how the construction for the transformer. But bear in mind, you can see that this flux A, right? A, this flux B, and flux C, they all meet together and cancel out to each other. So in theoretically, we don't need additional limb to conduct the neutral flux. We don't need to do that. They all cancel out. But of course, when the flux is unbalanced, in here, we assume all the 3 phase 100% balanced, but nothing can be 100% balanced. If they don't balance, then you can see that some flux, so the flux A, B, C in here, may not equal to each other. So in a way, eventually there will be some remaining fast transfer somewhere, which causes additional losses. But that's how we see it from vertical design. We try to make the thing perfectly balanced and coupled, but in real case, we are not that case. That is why in all the transmission system, they require all the system must be perfectly balanced. Only imbalance down to only 1%. If more than 1%, the PG&E will allow the transformer to be installed. So that's the system required. So that means in all the building, or they try to balance all each of the 3-phase to be equal current. If they don't equal, they have some inductor transformer to balance it out. If they're not balanced, when you connect to the PG&E, then they find that it balance more than 30%, they will give you higher charge you more electricity bill. So that's how the system works. So anyway, you can see that. Yeah. So in here will be another arrangement which tend to use 3 separate transformers to behave as a 3-phase transformer. So that's, you can see the arrangement, quite straightforward, how we connect that. In the primary side in here, then you can see that we are connecting in Y connection, right? Because we have common neutral in here. But in the secondary side, become a delta connection, which you can see that all 3 wires connect in delta, which have no neutral point. So that is to say you have many different ways to connect them anyway. So the good thing of this arrangement is, although we know the disadvantage will be erasing some transformer core, but we do have advantage. Sometimes because we can use single transformer to behave a 3-phase transformer. For mass production of milk, then we can actually manufacture many single-phase transformer to make up the 3-phase. Then when the production quantity is large, we can actually reduce the cost. In case any one phase is broken, we can just replace one transformer. But in this case, we need to replace the whole transformer. That is expensive. But we replace single transformer, we take this thing out, we connect, can save. So that's why in many cases, then this will do have some advantage. So which one is better depend on the application, how long you want to use it, and maybe the stress or whatever. There's a lot of the pros and cons. Any question up to this point? So here will be other advantage, disadvantage, cost effective, balance load handling, and also enhanced performance. And also voltage regulation. Somehow in each transformer, you can control each of phase voltage to make them balance. Because in theory, each of transformer will be identical. But sometimes when you install insurance system, the voltage in the input side may not be balanced. Even though you use 3 identical transformers, the output side is still not balanced. So you need to calibrate a little bit to make the output become balanced. In this case, you may need to choose 3 separate transformers. Each may have some calibration of some winding, adding one term and less one term to make the output voltage balance. So that's a way we can use this kind of the 3 separate transformer. We can still able to adjust something. So that means the more flexibility, you can able to adjust for more wide range of application. So that's how we see the cost effectiveness by using 3 separate transformers. Of course, in this case, the initial cost may be higher, but maybe the maintenance cost may be lower. And also you can see that easier for maintenance and also ground connection. We can able to create our own ground here quite easily because in here, you can just create our own ground in here quite easily. But for this transformer, there's no ground connection. Ground and neutral are really similar. So in this case, many cases, we want to protect ourselves. We need to create our ground connection. So, but for this transformer, we don't have this. We need to rearrange our ground. For instance, if I do a transformer like this, then you have low rate, you can create your own ground. So you need to recreate, you need to use a 3-phase resistor circuitry to create or additional ground. So that's something for different kind of the connection. We do have some advantage and disadvantage. Anyway, the next section, we'd like to discuss about the power losses. So power loss is, of course, most important. We'd like to see what kind of losses will be available. So when we have copper wire, then obviously we got the copper losses due to I square R losses. But another losses will be due to the magnetic material. So magnetic material, you highly relate to the B field, magnetic field density, the B. Another one will be the frequencies. So two major losses we like to mention to you. One is hysteresis losses. So all the BH, I think if you learn the electromagnetic, then you know that BH loop will be behave in such a way. It's not a linear line, but you can see that there's a loop in such a way. And then we also found that the losses for that hysteresis loop will be related to the area enclosed. So this area enclosed will equal to the magnetic losses. So these losses, we call hysteresis loss. So this is really common losses in electromagnetic. The detail I go to the material guide. I'm not going to explain to you the material, but for empirical formula, then you can see that the losses are equal to this one. Then we have our proportional constant. We also proportional to the B field. So you see here, I use the P value of the B field, but the index here, exponential index is equal to M. M is not equal to 2. Between 1.5 to 2.5 depend on the magnetic material, and also proportional to the frequency. Why is that? Because when we complete one cycle of the applied sine wave voltage, then you're looping in here. So once it pass through one loop, then it generates one losses. For high frequency, many times, then we got many losses like this. Yes?
Is K sub H a constant or is it a variable?
K is supposedly will be a constant, but still relate to the magnetic material, relate to the temperature as well. And somehow slightly relate to the frequency, slightly. So that means when you measure them, supposedly will be vary with a lot of the parameter. So basically for many data provided to you, we call constant. Yes.
So K is just the constant that just balances out the formula. Got it?
Then there's a number of ways we can just using this formula to calculate, even though some manufacturer, they might give you this formula for calculation of losses. But some manufacturer, they prefer to look up from the table, look up from their data. There's many different ways to assess the magnetic losses. So here we will just give you some initial understanding how the losses look like. The losses is really complicated. We need to manage it. So you can see that this formula only approximation. Never can be accurate. Only so magnetic losses usually calculate up to ±50%, also become really reliable. So believe me, ±50% also good. So because this formulation is not very accurate, but it's good enough for you to initially understand about losses. From this formulation, you can see that the losses is related to a constant, proportional constant, which vary with temperature or other parameters, and also relate to the magnetic field, but that usually peak magnetic field. We tend to use peak. And the index here, 1.5 to 2.5, typically with 2, and then proportional frequency. So that's the formulation. So M is thickness of potential. So these are fixed parameter. So we to do a lot of the measurement. Measure them and then try to using this kind of fit-in curve and then obtain the M. But this M, although may be equal to 2.1, 2.2, only within certain range of the B field and the frequency, not the whole range. So all the metal material are only suitable for certain range. When beyond this range, the formulation will become highly inaccurate. So that's how we see that. Again, because one of this kind of BH loop will call equal to one frequency or one period. So when you increase the frequency, so the BH will travel again for this loop. So that will one additional losses. So that is to say for hysteresis losses, higher the frequency, higher the losses. So that's to say for metal material, if you're working at 60 Hz, the loss can be very low. But when you increase the frequency, then the losses will proportionally increase in such a manner. That will be one of the big issues anyway, right? So that is to say all the metal material will say what's the suitable frequency range. So if that is for low frequency, we will say 60 Hz, whatever. For high frequency magnetic, some power electronic, then high frequency motor, that will be another way. So that means I mentioned for electric vehicle, if you go for high frequency motor or robotic high frequency motor, then the metal material must be high frequency. So to get the losses, typically just fit in the parameter, just get the losses or lookup table. So another losses we call it eddy current losses. Eddy current losses, I think you learn about eddy current losses, right? Have you learned them? Have you learned eddy current losses? Yeah, you briefly know about material, you know eddy current losses. At high frequency, when you pass through a magnetic field in here, you can see there was some current looping due to back in there. But the current will become a short circuit inside. Because the resistance inside the magnetic material is still iron conductive, then that's why we will create losses. If you don't want that losses, that's why you can see the transformer, we are laminated, a lot of the laminated, or they are solid iron. We seldom see transformer solid iron, because internally, the eddy current will pass through them, will create additional losses. So that's why you can see that all the commercial transformers, if you look inside, there are a lot of the plate. They are called lamination. Yes.
So are they like plates that are stuck together,
Stuck
or
together.
is it like cut?
They're all metal plate like this. You can see that, for example, like transformer, then you can see a lot of this kind of the transformer plate in here, like this. And then we usually have a former. I try to create experiment to you. I try to ask the technician to buy me some metal material, show you how to make a transformer anyway. So there will be, we have a metal core in here, just a metal core, like this. And then we put this thing inside here, right? Inside here. And then there will be many, we call it lamination, laminated steel. We put them one by one together, stuck inside until we fill up this called the former. You can see that all this laminated iron, they're really thin. So thin because the depth thickness are highly related, called another parameter called the skin depth. Have you learned anything about skin depth? So skin depth is one of the thickness for the material. So the under that frequency, the loss will be negligible. All this additional material, I left the geometric guide for Professor to fix. But bear in mind, you see that because we want to reduce the eddy current, then we don't allow the current inside flowing inside the solid iron. Instead, using solid iron as a magnetic core, then we use laminate. So that means each one of these things are laminated. So this coat, they have coating here. Don't think they're just pure iron. We have some coating, laminated coating, maybe like liquor or paint, to isolate that so that no current can be flow through between the laminated iron. So which you can see that I draw some line here, because inside you can see there's a lot of layer. Each layer are electrically isolated. So the current now cannot flow through them because stopped by the lamination. So that's one of the way we can reduce the losses.
Is that like a thin, like an E bracket that goes together when you have that transformer inside?
That's right. There's a lot of way you can do E here and another E here. I put them a bar here and then E, then a bar. We can just be stacked together. So I do highly recommend you to go home and you see any new transformer. Smash it, open up. You can see how the lamination. You need to do that as an electrical engineer. You need to know how to construct a transformer, right? Smash it to see how the lamination looks like. Again, if you do a multimeter to measure it, you can see that there's some kind of insulated material. They are not metal. They are not conducting electricity because they got kind of coating on the surface to isolate the electricity. So it's quite interesting. Something simple, but it's quite interesting. Open up, you can see all this magic. It's not really magic, but how we make up the transformer. Any questions? I guess you must have some use the transformer at home. Yeah, trying to understand what you can see the lamination. You can see all these things, interesting things here. But that is only for low frequency transformer. When I say low frequency transformer, the 60 Hz, this is frequency, we call low frequency, we use lamination. The lamination thickness usually really thin, I think maybe less than 1 millimeter, 0.5 millimeter. Because that's the thickness, you can ensure that there won't be any power losses. You can see that the current are looping here, but using lamination to stop it. But can the current looping in here, that's small thickness? So we're going to stop that. So we scientifically, we can see that when the thickness are thin down to certain thickness, the current cannot flow in that particular displacement, but that highly relate to the frequencies. So at 60 Hertz, then you can see that thickness should be down to 0 point something, and then the losses will be negligible. So this phenomenon, we call it skin depth. That's how is the thickness related to that lamination. So you can check the internet to say what frequency is what kind of skin depth. That is the way we design the lamination. So, but more importantly will be, of course, the skin and all the electron loss, we do a formulation. This formulation are again related to a proportional constant called Ke, and also proportional to the square of the B field, and also proportional to the frequency square. So the index here is roughly about 2, but it's not the fixed, can be varied according to the metal material. But this formulation only gives you a brief idea how the losses look like. It's very straightforward. It's a part. When the manufacturer gives you this data, you just apply the frequency and B field there, you can get the losses. But this only using approximation or formulation. But in more often, the manufacturer will give you a chart like this one. Then you can use lookup table to give you the total losses. So like the hysteresis losses and the eddy current two sum together become total core losses. So like in this diagram, we have the horizontal axis is the magnetic B field density. And then here will be losses. And this will give you different kind of operation frequency. So that means you need to identify in your application what frequency it is and what B field is, and look up the table, you can see the losses. So that's how we see it. And also you can see that in this chart, they also relate to the temperature. Say in here, 60 degree, 100 degrees C. So that you can see that the temperature relate to losses. That, as I mentioned before, relate to the K parameter, the proportional parameter K, right? And then relate to the frequency and relate to the B field. So usually the manufacturer, when they provide to you the formulation, they will use this part convert the formula to you anyway. So that's how you can see that more. I think you can use either method, but for me, I usually to use log table to estimate the power losses, because that is the actual measurement by the manufacturer. They will just provide to you. As I mentioned, all the formula is only an estimation only. So, any question up to this point? So here, you could do a very quick example. So we given that the proportional constant K is equal to this one. Now we operate at 50 Hertz, and the B field will be this, right? And then we calculate the losses. So from the formulation, we just directly pump in all the material number here. Don't have any special. And then we calculate losses for pH and PE, the summation of losses equal to this one. So that's how we use the equation. Very straightforward. We just use a formulation to get all the unknown parameter from the manufacturer. And then we just put into the equation. Then that's it. That's how we use it. Very simple, straightforward. No complication. So that's one method using formula. So usually if the manufacturer provide with you the formula, you just put in all the data here, you can get the losses. Straightforward. Another method will be, we can also use a log table. Like in here, the log table will say if we give any parameter, like if you want to say 100 kilohertz and what kind of density, and then you can also log table to get the losses. So either way, that will do. But to conclude what we have learned for this chapter, we see that transformer can be function as an impedance matching. We can match the impedance, now use n square, become the impedance matching. The main application can be like for speaker or something measurement tool, we need to match the impedance. Like an oscilloscope, we got 1 megahertz, we got 50 ohm, so we need to use something to match the impedance. Auto transformer is another one we learned here. Auto transformer using single winding to use as a primary side and secondary side. So what we learned here will be, firstly, you can reduce the number of winding, reduce the copper, and also could reduce the current inside the shared winding. Three-phase transformer can be constructed by 3 separate single-phase transformers. Of course, it can also done by using 3 winding in the magnetic core. And dot rotation is something we need to memorize. Without a dot rotation, we don't know the polarity. So especially important when we connect a number of transformers together. So that briefly what we learned. There's many material on the internet. I use this book, as well, but there's many other websites. There's some example website you can search up to understand more about the magnetic core and also 3-phase transformer connection. There's millions of material for that. So, any questions? Okay, this chapter just concludes what we have learned for last week. So we conclude our learning for the transformer. So next thing, we will go for the DC motor then.